Se está iniciando. Vale, ahora he encontrado bien. Hi, everyone. I see 4 people there connected. Identify yourself. One is me. You can do it in the chat. Baptiste is there. Hello, Baptiste. And there's still other people who must be probably connecting. Okay, Josep. So welcome to this class. As you see, I'm very happy because I have a whiteboard. And we're going to check if finally the whiteboard is as good as I think it is to teach. I only see 4 people connected, so let's wait a bit. Julia is there. And well, in the meanwhile, what I'm going to do is to recall. I don't know if you don't see, because I can read the chat, let me know. Okay, I'm going to be, I'm controlling from 2 computers how things are seen. So the first thing is the definition of symplectic manifold. We have an even dimensional manifold. And I have a 2 form, omega. Well, this is, you can see this. Maybe I'm going to put more light. Okay. So I'm going to try to write bigger in case you don't see this. So omega is a 2 form on the manifold, okay, which we require to be closed. Okay, we require this condition, and we also require omega non-degenerate. The condition of omega non-degenerate, if we think of this at a certain point, I think it's better. There are some reflexes. I'm going to put this down. I think now it's clear what is, you can see better what it's written, right? Thumbs up if you understand, if you can read it. Okay, so the condition of non-degeneracy was the condition that we could think of a condition in algebraic, in linear algebra, if we just evaluate this at a point, okay? Then this is a 2 form in the dual of the tangent space. Therefore, we may think that the condition of non-degeneracy means that if this condition is satisfied for all b in the tangent space at the point that I'm considering, okay, then the condition, if I have such a thing, then u has to be 0. So it's a condition that I can think of in linear algebra terms. That's the definition of symplectic form that we saw. All right. And then I'm going to try to change colors. This is black, so this should be quite clear. No, Jordi, still not a problem. I'm just trying to, as I see, well, now there are 11 people, maybe all the classes connected already. I imagine, because some of you are sharing apartment. So, so I will start with the problems in a minute. I'm just recalling the definition of symplectic structure, and I'm recalling that this definition, this symplectic structure, has to satisfy these two conditions. All right, and I'm recalling that the condition of omega, and that's an important remark, omega non-degenerate, is a condition that I can think of in terms, without evaluating this, I could just consider the condition that omega is a two-form defined on a manifold. This condition of non-degeneracy imposes the fact that the manifold is even dimensional, and we have the condition that omega n is a volume form. Usually we put it like this, omega in positive, it means that omega n defines a volume form. On the manifold. All right? In particular, this tells me that the manifold is orientable. So these are basic things that I already explained, but I want to recall because I'm going to need them. Okay? So this is orientable. All right, this is clear. This is just the basics, just the definition of okay. Now this is a reversible. This is reversible, but apparently the system is not working, so I'm going to just turn it around. And then I'll turn it around again, so I have the definition back. Okay, so now that's the basic definition. Now I want to look at the list of exercises. One of the definitions that I'm going to use, and that's very important, and that you will need for the test indeed that you have after, is the definition of Poisson bracket. Okay, this definition of Poisson bracket, we do this for a symplectic form, okay, associated to a symplectic form. Next Monday, we will see that it's possible to generalize this to manifolds that are not even dimensional and still admit a symplectic form. So the definition is, if you have, that's the Poisson bracket, associated to a symplectic form, okay, and the definition we had is apply omega, the symplectic form, to the Hamiltonian vector fields of F and G in this order. Okay, remember that omega, at every point I can think of this as a skew symmetric form, and I apply this on the Hamiltonian vector fields. I recall, for the sake of completeness, for you to have all the ingredients, what is the definition of Hamiltonian vector field? I'm going to put a minus sign here. In some books, you'll have a plus sign. But it's important that, well, I'm going to use this minus sign. You can change to the plus sign, but then you need to do consistent all the formulas. So this is the contraction. So I have the 2 form. This is a 1 form. All right, this is a 2 form. And now I contract this, and that's my definition of Hamiltonian vector field. Okay, so here I plug the Hamiltonian vector field of F and the Hamiltonian vector field of G, and that's indeed some properties that I checked partially, and I left one as an exercise. So this is the beginning indeed of the exercise session. Okay. Okay. So remember that this is something I left in my last video. that if I look at this, I can think of this as an assignment that assigns for a couple of functions just the bracket. Okay? And indeed, I could try to, if there is a possibility, to define a bracket that satisfies a certain conditions, also for manifolds that are not symplectic. In the symplectic case, the Poisson bracket is defined as such, and that's the Poisson bracket that it's used in all the books in classical mechanics. Okay. So the properties that we saw already. The first one, which is equivalent to Noether's theorem, so I'm also recalling it, is that the bracket of two functions that are the same is 0. Okay? We could think of this, indeed, we could think of this also as Noether's theorem, and this goes for Baptiste. This is exactly Noether's theorem in the symplectic case. Why? Because this is something that I checked from this definition. The other day we saw that we can also write this as a Hamiltonian vector field of F applied or acting as a derivative of the function g. Okay? Therefore, this formula, I could also apply it as the Hamiltonian vector field of H applied to H equal to 0. This means, in other words, that the trajectories of H lie on H equal to constant. And that's exactly the conservation of energy or Noether's principle. Okay? So that's just a parenthesis that we saw the other day, but I find that this is important. It's going to appear in the test today, so it's good. It serves this class as a review for the basic things that you'll see in the test. So that's the first property. How do you check this? Well, you check this from the very definition. This is omega applied to xh equal to 0. So it's a tautology because omega is a skew symmetric form. Therefore, when I apply it to two vector fields that are the same, it's going to be 0. Okay? Omega at a point is skew symmetric. So this property, which is which you see, this is a language, as I said, that can be useful to explain things in physics, and that's an example that explains Noether's theorem, Noether's principle, or you could call this principle the principle of conservation of energy. The energy is preserved. Okay, and for us, you see, mathematicians, once you have the right language, is a tautology. It's just saying that the skew symmetric point is 0, as a skew symmetric form is 0 on two vector fields which are the same. All right? Okay, this is what we call the antisymmetry. That's something we saw, but I thought it was important. The second thing is a Leibniz rule. And Leibniz rule, it means that I think of this, well, observe that we have seen that the quick way to check Leibniz rule is to observe that from this remark here, we see that the Poisson bracket is just the Hamiltonian vector field of F applied to G. So this is the Lie derivative of F applied to G. And because it's a Lie derivative, it's a derivation. It acts as a derivation. Okay? Therefore, because it acts as a derivation, it satisfies Leibniz rule. Okay? Because if I do the Lie derivative of a product, okay, because this is a Lie derivative of x to f applied to gh. I'm going to say that it's the derivative of the first term times the second term plus the first term, the derivative of the second term. Do you agree with me? Okay, that this is exactly because it's a derivation, and I'm applying it here. Okay, do you agree with me? Okay, so observe now the thing that we can do at this point is to translate back to the definition of bracket. Therefore, this can be written as FG H plus G F H. All right, that's the formula. You can read this formula. Yes, I can see it on my screen. That's the formula that I can call this formula Leibniz rule. Okay. If I put the G multiplying before or after this bracket, is the same because the product of functions is commutative. Okay. Any questions at this point? Okay, so I left as exercise the third condition, which is Jacobi identity. Okay, and there are two ways to approach Jacobi identity. I'm going to comment them. So 1 second, because I have to. So I'm going to comment. This is here. I have just the definition of the objects we are using. And now the third condition that I need to check is Jacobi identity. Okay. And for Jacobi identity, I need to recall, and this is something that most of you already know because you have done differential geometry either at the UPC as an optative or at the UV. So most of you know this. If you don't know this formula I'm going to use, well, you have to believe it. You have to believe it's true because I'm going to have to use it, unfortunately. Okay? So the third condition that I need to check, and this is the exercise that I had left, was what I call Jacobi identity. That's an exercise. Okay, and Jacobi identity is the formula that tells you that the sum, that usually you put it like this, to call the symmetric sum, is equal to 0. This means that I can write this in the long way, and I'm going to do this as the bracket of GH. And now you fix this element and you start moving. Next one will be G. Next one will be HF. Okay. Plus, next one will be H. And then I have F and G. And the sum of this is equal to 0. This is Jacobi identity. A way to prove this result, there are two ways, which are totally equivalent. Indeed, quite equivalent. To prove this result, the first one is to use, which is the one I suggested, is to use the fact that the correspondence between functions and Hamiltonian vector fields given by this formula defines an isomorphism of the tangent and the cotangent bundle. And indeed, I sort of mentioned that you can consider the bracket from the set of functions to the set of vector fields and check that this is a Lie algebra morphism. So that would be the first one. If you use this way, this is equivalent to checking, and that's an exercise that I left, that you can translate, okay, everything in terms of the Lie bracket, and then you can translate everything in terms of the Lie bracket, plus then you translate xh, xf, xg. That's the first approach. The first approach is a slightly longer, but interesting, because for that you need to know more than Cartan formula. You need to know for that, and this is, I'm going to use a quicker approach than this, but I'm going to leave the formulas that you need to prove this, is that the Lie derivative and the contraction satisfy, I write the contraction on a y, but it's a iota, of course, satisfy this equality, and that the Lie derivative of the differential of yx plus yxd satisfies this one. The second one is what we call Cartan's magic formula. And the first one is a relation that you use, and then if you just contract from, if you use these two, and this is a computation that I'm going to leave, it's just a computation, okay? And the trick is that you contract the bracket of x. Here I'm going to use the notation of the last day, because you can apply this h, capital H and K to be f, G, or H, no matter how you apply this is gonna hold. All right? So if you apply, if you develop first replacing the first formula and then replacing the second formula, and this is really a computation, you really get that this is the minus the differential of H and K. So this is really an easy computation, and this gives you that the bracket, this gives you a property that I also left as an exercise, that this bracket is exactly the Hamiltonian, that if you do the Lie bracket of the Hamiltonian of the functions h and k, then this is the Hamiltonian of the functions h and k. And this is exactly equivalent to saying that this is a Lie algebra morphism, and it comes from using these two formulas. What I say, I leave as an exercise. Okay, it's easy, but I think it's a good exercise for you. Now I'm going to provide a different proof. But this proof has the advantage that it shows in the way that the bracket goes to the bracket. Okay, and once you have this, you just need to develop these terms, and you reprove the result. Okay, and also this has the advantage that you prove that this defines a Lie algebra morphism. If you look at the list of problems, okay, which indeed I updated yesterday night, so now it's quite long. There is an exercise on the list that it's good that you look at it from this perspective, which is exercise number 10. In exercise number 10, we restrict to quadratic forms, okay? And very interestingly, if you restrict to quadratic forms on R2 and you take the LaRue form, okay, Julia doesn't see the, I'm sorry. Nobody sees the red color, or just Julia? Okay, I will skip. I will not use it. I'm going to read what is. I'm going to write this. Somebody comments that you cannot see the red color. I just wrote that the contraction of the bracket is minus the differential of the Poisson bracket. All right? And this gives me that the Hamiltonian of H and K, the bracket is the Hamiltonian of the bracket. So the Lie bracket goes to the bracket. You see it better now? Julia, can you see this? Okay. So that's the first approach, and in the way you prove more, in the way you prove this other intermediate itself. All right. Now I'm going to do a different proof, which is straightforward and just uses indeed Cartan formula. Okay, and it's quite short. It's just like this, so it's quite short. But I'm going to need to erase. I can erase, right? Well, you can always recover. I imagine that after this is going to be in the YouTube channel, so you can always look at this again. So this is the first approach, and then it's automatic because you have that this is satisfied because the set of vector fields satisfy Jacobian identity. Therefore, one Jacobian identity implies the other Jacobian identity. That's the whole thing. And another method to look at this, which indeed is equivalent because the formulas that I am using end up being equivalent, but it looks a bit shorter. So I'm going to write it here. The next one is to use Cartan formulas in the following way. So we use, now I have to wait because this is wet. We use a formula that you have seen. If you have not seen this formula before, you have to believe in this formula, okay? That tells you that the differential of omega applied to vectors b0, bk. So this is the definition of differential of a form. Indeed, you've seen this before because Joachim, the day he was replacing me, he explained exactly this formula, okay? And you get that this is the sum from I equal to 0 from minus I of the vector fields that now act as a derivative. So omega is a K form, okay? That's the thing. I'm going to skip. Omega is K form. So differential of omega is a K plus 1 form. So this formula tells you what is the differential of omega in terms of omega applied to all the vector fields, because here I have K plus 1, and we apply the definition of a K plus 1 form. Omega is K form, therefore this is K plus 1. And we apply this definition by taking subsets of K elements here and applying omega in a way. So how can we take subsets of K elements? Well, we can just avoid taking one, okay, that's a way to go. And then we have to do the vector fields that we don't put inside act as derivation, okay? Or we can pair them and then take 2 out, okay? And then it acts as a Lie derivative inside. Then you have a Lie bracket. And the formula is the following. I'm explaining the formula. But this is a formula that you have seen. So this is omega. This is the sum of bi over I, starting in 0, omega b0. Then I avoid taking bi, and I go to bk. All right? And then I have some other terms. I have to take care, and I start also with I equals 0, but I order I smaller than k. Then I have minus 1 equal to I plus j omega. And here I have the brackets that we can put at the beginning. Because here you have a change of order, of course. And then you take out the element bi. I'm going to leave for you to read, because I'm left-handed and that's inconvenient for this order. So you have these terms. You have either you take out a term and it acts as a derivation, because when you apply omega to these vector fields here, you have a function, okay? And this is just the Lie derivative of the function, all right? And then you have this term here, and then you have some other terms where you pair 2 by 2 inside and you take out the bi, all right? Okay, so now I'm going to apply this formula. Okay, if you have not seen this formula before, well, we have to assume that you can find it very easily. We have to assume this formula. Okay, then the proof is very easy, because I want to check this equality. Okay, and what I'm going to do is to compute. We would compute the differential of omega applied to the Hamiltonian vector fields xf, xg, xh. By the way, what I'm doing now is solving an exercise that I set in the videos, but I also added this exercise to the list of problems. Well, you have a video of the team solving exercise 12, and you have it in YouTube, well, you have it in the email, so you can just check it out, okay? Okay, so now I'm going to develop this formula. Now I apply this general formula to the case in which omega is my symplectic form. Okay, therefore, the omega is a free form, and this guy can act on three vectors, vector fields. So we are right. So I'm going to apply this formula in this particular case, paying attention to the signs, and then I will interpret everything. So I just apply things following this formula. Okay, I assume that this is I equal to 0, I equal to 1, and I equal to 2, in order to check if you have this minus 1 or not. And then what I get is the following. I get x sub f, okay, deriving omega. I have the first terms. Maybe I should. Now I don't want to do experiments, because the problem is that I'm left-handed and I should have moved everything, but you don't want to see what I did to have my computer matching the. You don't want to see how my house looks now, so I will not do any further change in the address. So let's call it address. Okay, so you have minus xg. Omega. What I will do on Monday is to move, because I'm left-handed, and then I will not cover what I write. That's a problem. So xf, xh plus xh deriving omega applied to the order. The order is important. Xf, xg. What are these three terms? Well, these three terms correspond to applying the formula, the three terms that you get from the first part of the formula, okay? Well, here we understand that this is a function because it's a two-form applied on two vector fields, and this applies as a derivation. All right, and now I have to add more terms here. I'll have three of them, because because I have the condition that I is smaller than j. So I can only have three. So the three remaining terms that I have with the sign are omega, xf, xg, xh, plus omega, xf. So xh, xg, all right, minus omega, x, f, xh, xf. Xf, no, that's g, sorry. Okay, there could be errors. That's why I'm trying to pay attention to what's written, because this is the way you avoid doing errors. Now I have this formula. Now I need to apply the formulas that are on the other side, okay, of the whiteboard. Which are these formulas? The key formulas is knowing that by definition, and I'm going to apply this by definition, this omega of xa, for instance, this term, this is by definition just the bracket of G and H, by definition of the Poisson bracket. Second thing I'm going to apply, okay, and this is that what we saw is that the bracket of F and G, you can identify this with X sub F applied to G. And you can identify this both terms. So each time you have a vector field deriving, like here, here, and here, you can write this indeed as a Poisson bracket. Okay? So I'm going to translate. And I'm going to translate this. Okay? That's the first thing I need to do. Okay, I'm going to translate this. I'm going to do this in 2 steps. First, I translate the first one, but I could do this in 1. GH minus X sub G applied to the bracket of F and H. Okay, and here I have plus X sub H applied to the bracket of F and G. Okay, then what happens with the other guys? Okay, with the other guys, what happens is that first I can identify, I'm going to use the previous identity, that the bracket of X F X G equals X of F and G. Okay, so again, I'm going to do this in 2 steps. So I'm writing minus omega. Instead of doing this, I apply the bracket of F and G. So the other formula I'm using here, I'm going to write in this wonderful color, magenta. I hope that you can see. Otherwise, you let me know. Here, yeah, it's quite seeable. So I'm using that the bracket of X F X G is X bracket F G. Okay, yeah, you can see it, right? Okay, wonderful. So I'm going to do this again in 2 steps. I could do this in 1, but okay, let's go. And then I can identify again with the formulas. So here I just apply that this is the bracket of F and G, F and H, and that this is XG. Sorry, that this is X sub F, X sub FH. Okay, and then this is X sub G. Have to pay attention not to make errors at this point. Minus X of GH XF. All right? So that's the first step. Any questions? Now I'm going to go up here. I'm going to continue up here. And that's what we want to prove. So I will not erase, but I will erase Cartan formula because I don't need it anymore. Okay? So I erase this. Indeed, this is the way we could just define the differential. That's the way to go. So now in this thing that I'm erasing, and because I see that this colored magenta is quite easy to see, I'm going to use magenta. I'm going to plug this, continuing the magenta here. So I continue here, and I need to see the same thing. Next step, I apply the definition of the Poisson bracket. Okay, well, this concept. So the bracket is X, F, and G. Okay, so that's the bracket of F by definition, GH. That's the first term. Okay, now the second term, we go on, and that will be the bracket of G, F, and H. Okay, and now this will be the bracket of H, F, and A, and G. All right, and now below, with a minus, now I apply the definition of the Poisson bracket here to every omega that I have on the second one. Okay, so I just get the bracket of Fg and H plus the bracket of Fh and G. All right, and the last one is minus GH F. And now I have all these guys, but I have to be a bit patient identifying what is everything. Look, if I look, I have this guy here. Now I need colors. I'm going to use green, hoping that you can see this. I have this F here, okay? And I have this guy here. You see? Yeah. I'm going to pair this guy with this guy. And I'm going to use the first property, which is that the Poisson bracket is antisymmetric. So this means that I can change this sign to a plus, and that this satisfies by 2 F G H. So we have this first term, you see, and we have it twice. And now I have to identify the G, F, and H. Okay, I have one here, and I have one here. Well, in order to see the same order, I need to do 2 changes, because here I have the F and the H, okay? Therefore, I should change the F and the H. And here again, this invokes a change of sign with a plus. But also, I will here with a minus. But then I have to change again the order of G and F, H. And again, this is skew symmetric. Therefore, we have a plus here and a plus here. And you have 2 G, H, F. Attention to the order. All right, do you agree with me? Say yes if you agree. I hope that you agree. You are very silent. Okay. Now what time is it? Yeah, we should be finishing soon. And I wanted to do more exercises. This is the most difficult one. Okay. So now I'm almost done. Now the last term is HFG, which I have here. Absolutely well ordered, and I have it here with a minus, so it's 2. Okay. HFG. Okay, now I'm going to ask. Anna agrees. Okay, wonderful. Now that Anna agrees, now I'm going to ask, what are we doing? We want to check that this adds up to 0. Okay? And we have developed the differential of omega, and we end up in twice what we want to prove. What we want to prove is this. But we need to prove that this is 0. How do we prove it? Who writes it on the chat? There are 20 seconds of disagreement between the actual YouTube, what I say, and what I see on the other screen. So come on, 2 seconds to tell me why this is 0. Okay, very good. Jordi says because you didn't use that omega is closed, but you wrote differential of omega. This is 0. At the beginning, I should have written that this is 0. We want to prove that this is 0. We have done this long computation, and this is 0 because there is a differential of omega. Very well. Okay? So, Jordi, you have, I don't know, not 1 point. I would give you a candy, but we are far away. Okay. So that finishes exercise 11. And that's the most difficult exercise that I wanted to do. I had, in my mind, I wanted to do 2 more exercises that are exercise 1. I'm going to do this very quickly because it's very easy to do this. Exercise 1 in the list is about coisotropic subspaces that you may think of. If I say coisotropic subspaces, it means that I'm working with a symplectic vector space. or you can think that this also works for a symplectic manifold. The difference is that the vector space, the form is constant, okay? Okay, so I'm going to do exercise 1 very quickly. Exercise 1 tells me that if I have a coisotropic manifold, let me see. That is a statement. We have a symplectic vector space. Okay, so problem 1. I did problem 11, now I do problem 1. We have a symplectic vector space. Okay? And we have to show that any codimension 1 Z be a codimension 1 subspace. Well, this reminds me quite a lot what I said about one-dimensional, what I said about curves on any symplectic manifold. I said that a curve on a symplectic manifold is always isotropic. So you may dualize this, okay, and you obtain, now I think that my internet connection is quite bad. Things are very slow, I don't know. I hope that you can read things. Do you hear me? My YouTube Direct is not working. I look at my face in the, and it's quite bad. Okay, I don't know. Well, I hope it's just an error at my home and that you are following. So what I was saying is that by the same reason that if you have a curve on a symplectic manifold, this is going to be isotropic. If we have codimension 1, this is going to be coisotropic. And this is the easier version because this is linear algebra. We have a symplectic vector space, but we could also think of a symplectic manifold, okay? We could also think of the symplectic manifold case. Yeah, guys, I'm sorry. There is a problem precisely at this moment with my internet connection and you cannot see it. So I'm going to wait for 20 seconds so this works again. The sound is okay. Yeah, I don't know what's going on. It has to do with everything is pretty slow. I'm sorry. Okay, I could say that that are things of the direct, right? So, okay, I want to check that codimension 1 subspace is coisotropic. All right. So, well, what does it mean to check that something is coisotropic? It means that I want to check that the orthogonal, that's a symplectic orthogonal, is contained on Z. Okay? Now what I'm going to do is to take, so I can check this, that's what I need to check. This is linear algebra, so I take a vector here. Okay, on the symplectic orthogonal. Okay, and I want to check that Z is codimension 1. So let's assume that Z omega is not contained, that Z does not belong to Z, and we will reach a contradiction. Okay? What is the contradiction? Okay, I'm going to do the following. I'm going to take another vector space, which is the sum of Z and the one-dimensional vector space generated by U. And I call this vector space over line Z. Okay? Okay, if U doesn't belong to Z, okay, then the dimension of this guy is the dimension of the symplectic vector space. You agree with me, right? So now what I'm going to do is to compute omega, okay, apply to the vector field U and any vector field that I write as X belonging to Z, and I take this combination. That's our vector. So I take I evaluate this against I. If we don't assume, sorry, this is a Z, and that's a U. If U is not in Z, then this guy is everything. Okay. So therefore, any vector on the manifold can be written as such combination. We are doing linear algebra here. Okay, now we develop this and I write this as omega. I am just using that omega is bilinear. Okay, now I have this expression here. Okay, and what happens? What happens is that U belongs to the orthogonal of Z, okay, and X belongs to Z. Therefore, this term, because they are symplectic or orthogonal, this is 0. And this term here is also 0. All right? Therefore, this is 0. Because I have to add ups of 2 zeros. But now, this would be any vector on B. Because then this guy, if we assume, therefore, this would imply that omega is degenerate, because from the definition of non-degenerate, remember that I have something of U different from 0 applied to any vector field equal to 0, it implies that Y is 0. Therefore, from this we deduce that omega is degenerate, which brings us to a contradiction. So the contradiction comes from assuming that U is not contained on Z. Okay, so I take here U any vector, so this proves that if I have a codimension 1, and here we have used here we use that it's Z has codimension 1. Okay, because then this generates all the vector space. So this is super simple, as you see, it's super easy. What I also wanted to do is problem 6, okay? But I'm going to leave this as an exercise because I think it's interesting for you, maybe. Julia? Okay, I'm sorry. There is a problem with my internet connection, apparently. 1 second. I hope now it works a little bit better. I'm not sure. Julia is the one who doesn't. Okay, Julia Baptiste. Okay, it seems that you cannot read, so I will take a picture take a picture of what you see here. Apparently there is a problem with some of the connections. I don't know which one. But what I'm going to do is to take a picture of the blackboard, as Julia is asking me. Okay, so I will post the picture on the website. It seems that now clearly there is a problem with the internet connection, and clearly it's not clear what I'm writing. So I don't know. You can hear me what I say. It seems that there is a lot. Okay, do you hear me? Okay, so what I'm going to do, I will continue. Let us. Okay, I think that I did my best for this to work. For some reason that I don't control, this is not working. I don't know if you are seeing this message. I have to stop now. I wanted to do exercise 6. What I will do is, I don't know, do a video of the exercise, of the resolution of the exercise, or do something, okay? But there is a delay, uncontrolled delay between what I'm doing. At the beginning, I think it was working well, but there is an obvious delay between my voice, the image, what you get, and I'm sorry, it looks like a disaster. So I will stop it here. I'm going to close this connection, and we are going to meet in Google Meet in give me 3 minutes to do the transition, okay? Okay, guys, it was a